Um, so yeah, a lot has happened in the field of AI, and generative AI is probably on everyone's minds. And the innovation there was almost shockingly simple in a way. It's just make the models bigger, like a lot bigger. And with all the new things happening and larger and larger models being available and companies like OpenAI dominating the space, I think it's fair to wonder, are we going further and further into a black box era with bigger and bigger models obscured behind proprietary APIs controlled by big tech monopolies? And as you can tell from the title of my talk, I don't think so. And I'll show you why. I actually think open source means that there's no monopoly to be gained in AI, and it's actually also what led me to found an open source company, Explosion. And some of you might know us from our work on Spacey, which is an open source library for natural language processing in Python. So basically bringing structure into unstructured text. And yeah, we've always, and Spacey was always really designed to be used in production, in real projects. And we've also always put a lot of work into API consistency, backwards compatibility, like all these really annoying things when you running an open source project. And this had a pretty nice, unexpected side effect more recently, which is that ChatGPT is actually pretty good at writing Spacey code. And yeah, because the library hasn't, a lot of the APIs haven't changed that much. You can, really ask ChatGPT to write the code for you. And another thing, another library and tool we're building is Prodigy, which is a modern annotation tool for creating training data for machine learning models by really focusing on real-world examples, and it runs entirely on the user's machine. And so that means that A, the data stays private, and B, you can also script it in Python and implement custom workflows for it. And finally, the next or third product we've been working on for quite a while brings the power of Spacey and Prodigy into the cloud. It's called Prodigy Teams, and it's a collaborative data development platform for cross-functional teams, currently in private beta. And the idea is it provides all the conveniences of software as a service, but has a private cloud component that the user can run themselves, so the data stays private, it's scriptable, and lets you implement modern machine learning workflows across the whole team. And actually a lot of the ideas and motivations I'll be talking about today really directly influenced the philosophy of Prodigy Teams. So, if you're here today, you've probably used open source software before. Maybe we can do a show of hands, like who has contributed to open source software before? Wow, yeah, that's good. And who works at a company that builds on top of open source or uses open source? Yeah, wow, that's like, that's a lot of people. So, open source is very popular, and there are a lot of reasons for it, and especially reasons why companies choose open source software. And one of them is, well, it's transparent, it's open, you see what you're going to get, you can look at the code, and it also doesn't lock you in. So, of course, choosing any type of software is always a commitment, but you'll never lose access to your work, and you can always pick it back up, and you're not locked in to a specific provider. And it's also extensible, like even if you want, you can take it, you can fork the code, you can build on top of it. And it runs entirely in-house, which is also really important. You don't need to upload any data or any code or anything to servers you don't control. It's easy to get started, you can just pip install, get going. And there's also a community vetting aspect to it, so you can see a project is popular, other people use it, and then use that to decide whether it's good and whether you want to adopt it. It's also programmable. Often, a tool needs to slot into an existing workflow, so you can program around it. And while that's not always the case, open source software is actually often quite up to date and current with latest developments that come out of research, and projects can move pretty fast because often they're actually maintained by relatively small teams, and they can accept community contributions. So, from people like you who've contributed to open source before. So you're more likely to get the recent stuff that's out there. And when looking at this, you might notice that one aspect that a lot of people usually associate with open source software hasn't even made the list, which is that it's often also free. And that's because I believe that companies don't primarily choose open source because it's free. It's a nice bonus. It certainly helps getting started and the community vetting. But I think companies really mostly use open source for all these reasons that are listed here, and it being free is just a nice extra. And so, of course, if we're talking about software in the context of AI and machine learning is not just code. Machine learning is code plus data. So there's been an ever-growing ecosystem out there of open source models and model artifacts that have been published. And I would say those artifacts and models, I would mostly divide them up in 3 groups. So one of them are task-specific models. So that's like the models and pipelines that we distribute for SPACY, or community projects like DAISY for state-of-the-art Danish NLP, or SciSPACY for biomedical data. Then Stanza from Stanford also published their models. And there are a lot of adapted, fine-tuned, specific models available. The customization is a big feature, so that's why I included it here. And task-specific models, well, they're often small, especially given today's standards. They're usually quite fast. They are cheap to run. But of course they don't, because they're trained for a very specific task, they don't always generalize well. And if you want to fine tune them, you need data for it. The next category I call encoder models. So that includes models that are trained on a large corpus of raw, unlabeled data, including Google's BERT and related models in the family like Camembert for French and Alberto for Italian, and I think lots of other nice bird puns. And these models often also power the task-specific models. I used as the basis, and then the task-specific layer is added. And these models are also relatively small, fast. They're affordable to run. Run in production quite a lot these days, and they generalize and adapt pretty well. But of course, you also need data to fine-tune them. And then more recently, the development on encoder models has led to a third category, the large generative models. So here are a few examples. Actually, before the talk, I was thinking, oh, how deep should I go? But I feel like even now, this list is probably already kind of outdated, and there's a lot happening in that ecosystem. But some examples are the Falcon model family, models published by Mistral, Llama-based variants. Stanford also published Alpaca for chat-related use cases. These models are, well, because they're large, very large, they're often significantly slower and also quite expensive to run if you want to run them in-house, but they generalize and adapt really well, and they need little to no data to use them for a specific use case. And so one thing that really doesn't help when looking at this is that pretty much all of these models of all these 3 categories have been called a large language model or LLM at some point or another. And that's confusing when talking about this. I think that also leads to a lot of confusion that people have when in this discourse, and that's also why I'll try to avoid this terminology and mostly refer to large generative models instead. Because actually, I think muddying the conversation by calling everything an LLM can be quite harmful, because there are really significant differences, especially if you're looking at encoder models versus the large generative models. So if we're looking at, hey, we have these models, how do they actually work if we want to make them do a specific thing? So with the encoder models, we have a task-specific network. So we have we have underlying encoder model that we train with a language modeling objective. Then we have these vectors, and these vectors we then use in the task network to predict labels for whatever we're trying to do. And together, that makes up our task model that then takes a text as input and outputs, say, some structured data like a category for the text. And then, on the other hand, the larger generative models, here, as you can see, we don't have a task network. We have the model, and we can prompt the model for whatever we want it to do, and based on that, we get an output which is also raw text. And then if we don't want raw text in a human readable format, but we want, say, structured data, what we have to do is implement a parser and parse out the structured data out of that human readable free text output. So that's kind of that's how it works, and also we can use a template for the prompt for a specific use case. So the way it works is quite different. And going back to the models, what we see is the task-specific models and encoder models, they've been pretty established. A lot of people use them. They've actually been in production at a lot of companies for years. And many companies have also started either experimenting or already adapting the large generative models. But of course, one difficulty is that these models are larger. They can be quite expensive to run if you're doing it yourself in-house. So there are a lot of providers that you can use that offer models, including a lot of the models that are available open source behind an API for per request fee, so you can query them and don't have to run them yourself. And so, why, like, if these models are available online for free, open source, how is it that there's, that there are companies, that make money by selling access to them? Well, the simple reason is economies of scale. So companies like OpenAI or Google, they're very large and they have some advantages here because they can hire the best people, they have access to compute at wholesale prices, OpenAI through the partnership with Microsoft, Google because, well, it's Google. And there are also a lot of other, more boring businessy reasons why, bigger is cheaper. But in the context of AI specifically and large models, there's also the API request batching that they can do. So if the model needs to run on GPUs are extremely parallel, but you can't just take the user's input and chop up the words to batch them up because the order matters. So you can either wait until you have a batch together, or you have a popular API that a lot of people use, so you get that high traffic. So so either you have latency, or you have the traffic or the cost, and so you can kind of think of it a bit like a train schedule. In a big city, you can have a train that comes every 5 minutes because there are enough people, and that makes sense. But if you're in a small town, it's absolutely not viable to have a train run every 5 minutes and run empty. So the train might only come 1 hour every hour and basically wait until there are enough people to transport. So yeah, that's how it works. And actually, if we're looking at this, if we're having a lot of companies that are essentially competing on price in the API market, that's actually kind of the opposite of a monopoly. It's competition. But still, so what are you going to do? You're here. How are you going to keep up with this? Are you doomed? Well, not quite. So if we are, looking at this, one other distinction I want to make that's also important is between human-facing systems and machine-facing models. I think this is actually something, if you follow the general discourse, this is something that's really glossed over quite a lot. And it's, you know, we always talk about AI in general. And I also think that's really what a lot of the confusion about companies monopolizing AI is based on. It's based because we're not making this distinction. So human-facing systems, you know, that's stuff like ChatGPT, Google's Gemini, and then we have machine-facing models that are GPT-4, BART, that are basically the underlying models of the human-facing systems. And for human-facing systems and products, yeah, the most important differentiation is actually product, not technology. So that includes stuff like UI, UX, how the product feels to use, how it's marketed, how it's presented, and also stuff like customization around it. Like, we don't fully know how ChatGPT actually works under the hood, but it likely implements a lot of constraints around, say, the model and the prompt to also prevent it from producing content that's offensive and you know, otherwise bad and makes people not want to use the tool. And then on the other hand, we have yeah, the machine-facing models. Those are really swappable components, and they are based on openly published academic research, and the impacts are quantifiable. So we have things like speed, accuracy, latency, cost, and so for every proprietary model that someone has built in-house, there's usually a corresponding open source model that's based on the same research, because, you know, that's all open. You know, not saying that training large models is trivial, but ultimately, well, you just, the knowledge is public, you just need to train it. And now I could see you're looking at this and you're like, well, but what about the data? Don't OpenAI and Google have an enormous amount of user data that they've collected, they've been to market early. Doesn't that mean they basically have can build better AI? And the thing about the data, especially the user data, is that yes, user data definitely gives you an advantage for product, but not for the foundation of the machine-facing task. So if you know how people use ChatGPT, there's like tons of stuff that you can do to make the product better and better tailor it to the user's needs. But one thing that we've really learned, especially from the developments in the past couple of years, is that you don't actually need specific data to gain general knowledge. And so that's, you know, that's really kind of one of the important lessons we've taken away from the development of the large generative models. And if we are talking about AI more generally, you know, what we usually mean are not a chatbot product, because, you know, hey, OpenAI might very well dominate the you know, the market of chat-powered, AI-powered chat assistants. That's definitely true, but they won't. You know, but that doesn't mean that they will monopolize or you know, win at machine-facing models. And you know, machine-facing models, that's really what we want to be looking at. And if we're actually thinking about, okay, how do people use these models? What are people doing with these models? What are the use cases in industry? There's another distinction, but again, also an important one that I think people gloss over, which is the distinction between generative tasks and predictive tasks. So generative tasks are things like summarization, reasoning, problem solving, question answering, paraphrasing, style transfer, and these are things that the large generative models really only made viable. We could do it before, but not as well. So these are all really new capabilities that we've unlocked. And on the other hand, we have predictive tasks. That are things like text classification, entity recognition, relation extraction, coreference resolution, grammar, morphology, semantic parsing, discourse structure. So in these cases, we have text that comes in, and instead of producing a human-readable text output, we produce a structured output. And usually that's then fed forward into some other process or some other application. And if we think about it, of the types of things people are doing in industry, one thing we'll notice is that many of the industry problems actually haven't changed very much. Not like even since before the introduction of computers. We really want to, like, one of the core things that we're trying to do is bring structure into things. And the main thing that's really changed is, yes, we have a lot of new capabilities that we can use, but we also want to have a lot more options for bringing structure into data. Because if you're working with index cards, there's kind of a limit to how much you can structure, and there's also a limit to how many projects your team or your company can do at any given time. Whereas if, with the help of technology, you can do more. So while there are new capabilities and new things we can do, there's also a lot of the same stuff we've been trying to do all along that we're finally able to do, and that we're finally able to do at a larger scale as well. And so, yeah, how do we do that? How do we tell a computer what to do? Because ultimately, if we're all here because we're trying to solve this fundamental problem, which is telling computers what to do. That's like at the core of everything we're doing. And there are different ways of doing that. In the beginning, what you would do is you would tell the computer what to do by writing rules and instructions. So that can be conditional logic, regular expressions, or any other rule-based logic that you can implement. And then with the advent of machine learning, we unlocked a new way of telling computers what to do, which is programming by example. That's also often referred to as supervised learning, and we can basically show the system examples where we know the answer, and then hopefully it will generalize based on that and do the same for things it hasn't seen. And then now with in-context learning and large generative models, there's an old but new way that we can add here, which is rules and instructions in the form of prompts. So we can write a human readable instruction and receive back an answer. And instructions are really nice because they're inherently human shaped, and they really, especially prompts, they really mimic the way we would tell a human what to do. And also, especially for prompts, it's very, very easy for non-experts to get started because, yeah, you just write up what you want the system to do and don't have to, think like the computer. But of course, there's also the risk of data drift. So if your model or if your data changes at any point, your rules or prompts might not apply anymore. And it can be quite difficult to figure out what you should do to fix this. And especially in the case if you have only limited insights into your model because your model is a black box. On the other hand, examples, they can really let you express very nuanced and intuitive behavior. Like often you see something and you know it's right even if you can't necessarily put it into words and describe in detail what the actual rules are for why you want it that way. You just know it's correct. And examples also make it easy to specify behaviors very specific to your use case, because instead of describing it in broader terms, you can actually just say, here's an example and here's what I want. But a big problem here is that creating these examples can be, or often is, very, very labor intensive. So that's one of the biggest bottlenecks, and that's kind of what's been holding this back. Like creating lots of examples for a problem takes longer than writing a more general instruction. And so ideally, of course, we kind of want to combine the best of both worlds into a practical workflow that we can use. So how can this sort of thing look in practice? Like what can we actually do in a workflow example that also fixes, solves some of these issues that we've identified before? So here's a quick practical example of stuff you can do. So on the one hand, we have a large general purpose model that has tons of weights and can do all kinds of things. And then we also have a large pile of domain-specific data. And of course, in mind, you have a problem that's very specific to your use case that you want to solve. And now with prompts, so rules and instructions, we can basically ask the model to produce an output using all the weights that it has to find the answer. And we can also continuously evaluate it. So we can benchmark and see, okay, given the correct answers that we know, how well does the model do out of the box when we just prompt it? Because that's important, and that's also a baseline you want to beat. And often, you know, it can be surprisingly good, but inevitably a model is going to make mistakes. So you want to have a way of seeing that, and you want to have a way of correcting that. So one solution that we found incredibly useful is having an iterative model assistant workflow for data annotation. And here, yeah, the example you see is from our tool Prodigy. This really can address the problem of labor, example creation being so labor intensive, because instead of creating all of these examples from scratch, you're basically just correcting what the model gets wrong and are reviewing really only the task-specific examples that you've identified. And if you're saving those, what you end up with is just kind of the portion of what the model can do that is also relevant to your problem. And based on that, you can then use this specific information and train a distilled task-specific model for what you're trying to do. So, you know, as you can see here, you're basically extracting, in a way, only the parts that you are interested in. And with the help of transfer learning, which lets you basically initialize the model with, you know, general knowledge that's, you know, you've gained from raw data, you can, you know, you basically don't need that many examples in order to have decent results here and also beat your baseline. So in some experiments, we found that actually even just a few hundred examples can be sufficient to beat or significantly exceed a baseline that you would get out of your prototype. And you know, transfer learning was one of the things that really you know, motivated deep learning and you know, was incredibly promising starting, say, 2018, and since then the focus of research has obviously shifted because there's so much happening. But this doesn't mean that transfer learning as a technology is outdated or has been replaced with in-context learning. It's basically just another technique that you can use that maybe you just hear less about because, you know, there's new stuff happening. So that's incredibly powerful. And you know, to give you an analogy here, you know, you can think of it like, let's say you're running a shop or you know, a coffee shop, and you want to hire a new employee. Like, of course, you expect that you need to teach them about you know, your business logic and how everything works, what products you sell, and so on. But you want them to come in and already you know the language and know how to have a conversation and, I don't know, be able to calculate basic things in their head. The other, like, while it's possible to train a new model from scratch just with examples, that's like, you know, training a completely blank slate person to do a job at the coffee shop. So basically raising them from birth, which, you know, is this is a lot of work, and usually the results are worse. So, you know, we don't have to do that. We can use existing knowledge and then take even more knowledge and distill that from what we can get from a very large general purpose model. And one thing that really also I think doesn't get enough attention, and where I think the large general purpose models really shine, is in the prototyping phase. So previously, you know, you really needed at least 40 hours of work on data to even get to a point where you had a model that was kind of shit but was like doing something. And then you train and you get accuracy 0, and you're like, is it because my data is bad? Is it because I have a bug in my code? Are my hyperparameters bad? And you know, that's you kind of get stuck there after having done all the work. That's something that you can really bridge now, the cold start problem, because you can start with a prototype that might be slow, might be a bit crappy, but can produce something. So in your prototyping phase, you can start out with a large model, run it, and extract and use it as part of your pipeline. So as an example, this is something we implement in the Spacey LLM extension we've built for Spacey. So it uses the components, pipeline component system. So you just have a component that you can plug in, and that follows the same API and can be powered by any large language model, for example, via an API, one that you run locally, and it takes care of templating the prompt using whatever the latest best practices are, and it also takes care of taking the response and parsing it into a consistent structured format and data structures that you can work with. So during prototyping, you can basically have a system that behaves exactly like your production system would and might use a model via an API. And then while you work on your pipeline for production, you can swap, replace, mix and match components, combine them with rule-based systems, and essentially end up with a series of distilled components that run fast and efficiently, and that produce a structured machine-facing object only for the parts that you're interested in. And so, looking at these, so what are some of the advantages that we have here? So, on the one hand, we can end up with modular components that are, basically that you can swap out, that you can treat independently, and modularity is a big core of programming, and it's how you want a system to work, and that's also true for your AI system. And you also don't have a lock-in. While you can use any model during development time, if you own your components during production, you'll never lose access to the weights because you have them. And even if someone switches off the API or if the model changes, those are all things that otherwise would basically lock you out of your own models. But if you own them, you don't have that. You can test components independently in a modular architecture, which also gives you a lot of insights into how they behave, because if one component isn't very accurate, you can work on it independently and really see where the problem is, which is otherwise quite hard if your model is a complete black box and does everything together. And it's also extensible. You can, add other components, add other, pieces of software that are relevant to your application. It's flexible, and it's actually quite cheap to run because if you're looking at some of the results, like I think a case study we did recently, they ended up distilling components that were under 10 megabytes, and they run super fast. Depending on how you build it, you can run it on a CPU, which of course is much cheaper, or a single GPU, like you're looking at very, very different dimensions here. And you can also run them in-house, which is very important if you're working with data private use cases, and in general, like, if you don't have to send your stuff to someone else, why would you want to do that? So, and if you can run it on a single GPU, you can really, it's much less operationally complex, and you can run it yourself. And it's also, you also want a solution that's programmable, because often, well, most of the time, you're very rarely doing machine learning for the sake of machine learning. You usually want to, you want to get the predictions from a model, and you want to do something else with them afterwards. And that can be very limiting if all you have is an API to work with, because usually there's code before and there's code after. So if you can program with your production system, that's very helpful. And you also end up with predictable and transparent output. Your system only does one specific task, and you don't have to worry about a lot of things that people are rightly quite worried about, which is what if my model has access to data it shouldn't have access to, or gives someone else access to stuff it shouldn't mess with. And so, here you have a component that predicts a thing and it can't do anything else. And so having the system that's a lot less operationally complex while still more accurate is very, very helpful. And yeah, so if you're looking at all these general points here, you might notice that these actually quite similar really map well to these points that we saw previously on why companies are using open source. And that's not a coincidence. Ultimately, yes, AI development might be different in its specific, but it's still a form of software development, and there are many best practices and things that we have identified as very desirable when using and working with software, and that includes stuff like modularity, not being locked in, and so on, that also extend to AI. And there's just because things are changing and we have new technologies available doesn't mean that these things are suddenly not true anymore. And you're probably familiar with the Zen of Python. If not, you can try it out in your terminal. These are just a collection of principles. It doesn't mean we have to religiously live by them, but I think a lot of that is very true and really expresses the core of what programming is about. And just because new things come up and even maybe new paradigms of AI development, it doesn't mean we have to completely abandon and throw away everything that has worked for us and that we know and be like, hey, new paradigm, baby, it's all different. Like these are tried and tested principles of software development that make a lot of sense. And I think, with the right tooling and the right approach, AI development can also keep making sense. So, to get back to our initial question that we had about, well, is anyone going to monopolize AI and how does that work? So generally, there's been a lot written about how to best establish a monopoly position and get rid of all of this pesky competition that companies and investors hate so much. And usually you want to tick as many boxes as possible and build your monopoly position that way. And one of them is you want to have a compounding advantage. So of course, network effects is one aspect of that. That's not really relevant here, but that's stuff for, say, Facebook as a social network or Google for ads. If people are using it and it's kind of the one place where you connect and that people visit, that can be very helpful. And another one is economies of scale. But we've already seen that actually economies of scale is a pretty weak or pretty lame mode for a monopoly because it's still a competition on price. Scale doesn't actually have that much of an impact because it's also not that expensive to compete. Like, this only makes sense if, or it doesn't make sense if anyone else can just come in with a bunch of money. And if you think about the dimensions here, it's actually on the scale of things, on the scale of operations and human endeavors, this stuff, AI stuff, isn't actually that expensive. Like, I think the Airbus A380 cost 25 billion to develop. The Tesla Gigafactory in Berlin was 5 billion. That's the sort of scales of money we're talking about for traditional manufacturing. And compared to that, like AI isn't that expensive. It's not that expensive to join in. So economies of scale. That's a very, very weak monopoly advantage. Then one option is, well, controlling resources. That's not really a thing here. We don't have any buildings. We don't have anything we're mining. It's not like the telecom owning all the wires in the buildings in Germany. So we can ignore that. And then there is one that's very appealing and that a lot of companies would love to take if they can get it. And that's, you have a monopoly because the government says so. And if you can make regulation happen, well, that's awesome. And the thing here is that hey, this is actually something we have to be quite careful about, because so far, the regulation that I've seen has done reasonably okay at making that distinction between the human-facing products and the actions and the things, that should be regulated, and not just focusing on technology or machine-facing models. But we definitely, we have to keep an eye out on this one, because if we do end up vaguely gesturing towards software and trying to regulate that, that's really how you can gift someone a very undeserved monopoly in a field that actually can't be monopolized. So to summarize, I think we're on a good path, and I don't think the AI revolution will be monopolized, because the software industry in general that we're in, it doesn't really run on some magical secret source that's internal. Knowledge gets shared and published. There's everything what we're doing here is based on research that's public, and that someone is going to publish eventually. So, and secrets are not what gives anyone a monopoly in a field. And similarly, usage data, hey, that's a great resource for improving a product and really establishing a very solid market lead in a product space, but it doesn't generalize. Again, what we've seen is you don't need specific data to gain general knowledge. That's what, a lot of what we're talking about here is about. So data itself, it will also not give anyone a monopoly. And large language models, or what, whoever, like what people want to call large language models, they can definitely be part of a product and a process, and they can be swapped out for different approaches. They can be distilled, they can be modified and used during development time instead of at runtime. And this kind of interoperability, which is also really at the core of what open source software is about. That really is the opposite of a monopoly. And finally, yes, regulation that could definitely give someone or gift someone a monopoly if we let it happen. But what's important here is that regulation should focus on products and actions. Those are the things that should be regulated and that are regulated, and not just vague software components. And that's what's important, and that's what we should keep in mind. And if we see big tech leaders speaking in front of Congress, warning about the dangers of AI and trying to regulate AI software in general, they might not be fully pure of heart, and that's exactly what we need to watch out for. Thank you.
Thank you so much. Ines, we have a question. What is your point of view of European AI Act, and how it impact the further development of AI?
Yeah, so I have to say, I'm not a full expert on the EU AI Act. So one thing I have noted, which I think is good, is that it definitely makes that distinction, which I think is important, between products and actions and the actual use cases and just technology in general. So I think that is a move in the right direction. Otherwise, I really want the EU AI Act to work out, and because I am pro-regulation, and I think the EU is playing an important role there. I just think it's important that we don't rush things and end up with regulations that are kind of achieving the wrong thing. Like, in hindsight, it would have been better to just ban targeted advertising instead of what we have now, which are like these cookie pop-ups, right? That's in hindsight. And if we end up with doing something similar for something like AI, this could have similar consequences. And also, I would really hate for people to use this as like an example of saying, like, see, the EU, they're just about regulating how bent a banana can be, and it's all like this bullshit, and we should just all exit the EU or something like that. So
but not too much Wild West as well.
Yeah. So
yeah. Next question: monopoly? Sure, not. What about oligopoly?
What?
Oligopoly, like oligopoly.
Oh, again, like I think a lot of similar points that I haven't really thought about this in detail, but I think a lot of the points I made about like open source and how software works, that's that's the opposite of a monopoly, but also the opposite of like an oligopoly. Like, you still have, if we are following these principles, you still keep all of those influences, out. And yes, it's true. It's not just big tech leaders, also, oligarchs lobbying. That's kind of a similar thing.
Actually, it's a comment, not a question.
Oh, yeah.
The next one.
Oh, next one.
I will read it. I think the real risk is not a monopoly, but instead a situation where control is held by a small number of large bodies. Only those companies that have resources to collect and process the data necessary to train large models can actually do so. Yeah. Any comment to comment?
Yeah, yeah. Oh, but I mean, actually, that is like, I think this is kind of something I also had in mind when making that monopoly argument, because, again, if we buy into this idea that we need to train and use the largest possible generative model out there and do all of that stuff and replace all of our existing machine learning workflows with it, then yes, we're gonna have a hard time, and that is the narrative that's also pushed by people who have an interest in that. But I've also, I try to show that, hey, that's not the case. It looks very different if you're using an open source model, say, at development time, because that actually, then you're less dependent on economies of scale, and then you can actually totally operate that yourself. You do not need anyone to operate the model for you. You also, open source means you do not need anyone to train a model for you. It's all, the knowledge is out there, the research is out there, so that's kind of, way against that. But again, if we, yes, we could end up gifting a small select number of large companies a monopoly, or like this kind of favorable position, and we should not be doing that.
Okay, we are going to blockchain a bit in the next question. What are your thoughts in comparing this current AI hype to the fanatical or financial interest in Web3, metaverse, crypto technologies? Of course, AI is here to stay and has been here a while, but do you have a feeling that the utopian promises are equally hollow?
Yeah, well, I mean, there's certainly an aspect to that. Like, it's also, I was actually kind of like, well, I'm not an expert on blockchain or Web3 or anything. I was actually kind of happy when this happened, because all these like idiots who were previously in like AI meetups and like being annoying, they all moved on to blockchain, and so I was like, great, but they've all come back now. So it's like, it's kind of
circle of life.
Yeah, there's always that aspect of it, and yes, that's also I think why I'm advocating for just critical thinking or reasoning about it, because there is so much that like the technology can do, but no, it's not this promise of magic. And actually, I don't know if any of you have been around since kind of the first chatbot wave and chatbot hype. I actually see a lot of similarities there. Or when deep learning first became a thing, first people were like, everyone was excited. It was like, oh my god, this is gonna change everything. And then people started adopting it, and they were like, wait, but why are my models all so slow and shit now? And it's like, well, yeah, because it's it's different from linear models. You need to use it slightly differently. And then slowly people have adapted, used the technology, and now we're there, but
on the curve.
Yeah, kind of on the curve. And yeah. And yes, there were also there was, I don't know if anyone remembers the IBM Watson ads from like back then, when with this glowing brain, and they had this guy from Mad Men do this like show at like World of Watson in Vegas. And no offense to IBM, they have like good tech, but like I'm still that campaign made me roll my eyes a bit. And I do think that sort of messaging is also what misled some people. This whole like, oh, magical AI, people bought into that, and now that happens again, and then people will see, well, sure, it's always work. Like if you want to do something that delivers a lot of value, you usually have to put work into it.
You have to be curious, but also filter some information that comes up.
Or actually another analogy is like, actually, I don't know if any of you work on the web, but I see a lot of analogies as well to the development of the web. So, and also how people are talking about, do we still need developers and stuff like that? It's like this idea of lowering the floor versus raising the ceiling. So yes, everyone in a grandma can now do a website on like Squarespace or Wix or whatever it's called. And, it it lowers the floor of entry, but then at the same time, web development is, bigger than ever, and you have people pushing the boundaries on the other hand side of like what browsers can do, and if you're Netflix, like I don't know of how much money you invest in making your player like 0.1% faster, and to how much money that translates into. So that's quite similar.
Expanding the environment.
Yeah, and it's like it's very easy now to maybe add some AI capabilities to your product, but that means that hey, if you have a valuable use case, you're still going to work on that.
Okay, what's your opinion on using copyrighted data published on internet to pre-train LLMs, NYT versus OpenAI and Microsoft?
Yeah, I mean, I think it's definitely this kind of very unfortunate gray area at the moment that, I don't know, people just sort of ignore that, like, oh, we just scraped the internet and we have, like, the pile and it's all, like, not our data, and that's kind of, normal, and we have to accept that. I do think this will be regulated more, and I also think that, again, it's not, there's sort of I think we will probably look back at this time as, like, sort of the golden age of when you still had, like, sort of unadulterated data to even train models from, because the internet's just going to be poisoned with AI-generated content that will then feed back into the models. I mean, I think ideally, yes, you want to use data that you can use. The only problem is, where does it come from? Is it representative? I do think we kind of have to accept that at least some of the weights that are out there trained on the pile are kind of what they are. But again, as I also said in the talk, I don't think we need to imagine a future where we need more and more and more data to train more and more of these models. I don't, yes, there will be some training happening, especially in research, but like all the interesting work is on how can we maybe distill knowledge out of those models? How can we have workflows that better use them for specific problems? And that shouldn't require just scraping more data off the internet. That's like sort of the least interesting part of all of it, in my opinion.
Great, keep on coming. Someone is typing the question, so maybe there's a question from the audience as well. Like you can raise a hand. We still have time. Yeah, go ahead, Luke.
You say we do have a lot of information about how to make the LLM recipe, and we don't need much more data, but there is one bit that we know shockingly little about, especially about the code, which is the reinforcement learning for human feedback. So maybe we can make a good misrole, but to achieve the level of performance that GPT-4 has, we need to unlock that piece. Is DPO enough? And second piece, of course, you have amazing tools like Prodigy or Gilla, even Lilac now to do data curation, but these products such as ChatGPT allow companies to widen their moat because they can build and have human label the data, so the data creation process is up to different scale compared to ours.
Yeah, no, I mean, it's definitely, these are like, I think especially a lot of that also feeds into the product aspect as well, though, because, a lot of what this is like relevant for is like, the chat experience you have in, say, ChatGPT, and like how to really take this model, which is basically just this sort of these raw weights, and really make it perform well in that context. So I'd kind of put it half into the product category, and then some of the is the technology, and sure there's still also processes around how to really best train and schedule these jobs and stuff. I think that's still those are kind of small internal processes that companies will have as their own business secrets. Like part of that is true, but I still think if you're looking at a lot of the use cases that are around bringing structure into data and what people are actually doing with it, you are now actually able to do these things by training on very, very few examples that you can totally generate yourself, and then the bottleneck becomes how good are these examples, and that's something you can fix with tooling. And that was my point around it. And sure, there's always going to be work on how to build large language models better, but I think there's also this other much bigger area of, hey, we are already there, we can already do so much, and the answer to all the problems is not throw everything away and wait for a model that's so big that it can do as well enough. So that was the main point. But you had good points, definitely.
Okay, one of the final questions from Discord: software engineering versus AI engineering, which has good future?
I mean, it's kind of, it's all sort of, the same. But and I mean, I don't know how other people are seeing it. But I actually think a lot of the skills that are really more core to software development, like really how to think about a problem, how to decompose it, how to write things that actually work well. That is really important. And yes, then you can still know about AI. But if I'm looking at successful projects we've seen developed in companies and teams, the most successful projects are actually those where someone came in with knowledge from say, a domain and from a use case, and basically, or came in with like a nail and was looking for a hammer and kind of upskilling in the area of AI and ML, rather than coming from ML and I'm having a hammer and looking for a nail. That doesn't really work out. And
I do agree with you. I'm working in this area as well, and I'm looking at that software engineers are looking for different kind of careers as well, and they're switching to data engineering. So why not? Could be a good feature to go.
Yeah, I think it's like if you have the foundation, you can always
Still have the foundation. Yeah.
Yeah,
just to
yeah,
mention.
but like if you can't program, then a lot of things are quite hard. So yeah.
Okay. Any final question for Ines? Everybody's. Yeah, it was great speech. What can I say?
Thank you.
Thank you so
Also,
much.
I brought stickers. So if you want to meet me, I have stickers until supplies last.
Thank you so much. So yeah, one minute. Could you?